So, from Japan, I'm Kiichiro Katsumata from Japan, from Japan. I'm so excited to come here again following last year Kaga event. Even I'm wearing green shirt, I'm not the organizer. Please do not ask me about this event, please. So this year, Drone Japan will present the gyro simulation system before a real flight. So this is to expand our pilot more and more across countries, saving time and cost. So please let us present the more details from Sunohara-san and Shibuya-san.
Okay. Hello, all Japan. And I'm Sunohara, CEO of Drone Japan. And today I'll be presenting on FFT GYRO and its integration with ArduPilot. So first, what is FFT GYRO? FFT GYRO is a system equipment that uses a 3-axis gyro to simulate an actual drone in an indoor or other environment. Until now, actual test flights of drones have always been risky with risks such as crashes. Furthermore, flight durability tests are costly, and adjustments such as pre-shipment inspections and tuning are time-consuming. With FFT gyro, these risks and hassle can be carried out indoors, significantly reducing them. Let's take a look at the demo indoor video. This is in stabilized mode from manually with the afterbar controller. First, the yaw is fixed version. Please excuse the slightly lack of synchronization. And next, the yaw is free version. So this system equipment is based on Eurekdynamics, a Mexican company specialized in the aviation industry, and Aeston, a Japanese company with strengths in aerodynamic analysis, is improving the system of hardware and software. So Drone Japan is also providing development support for ArduPilot integration, allowing the system to be used in various modes, such as alt hold, loiter, guided, and alt. So Shibuya-san will provide a detailed explanation of the technology and its future scope.
Yes, so let me explain our work. So first, to recap, why use FFT gyro before the first flight? So first, safety and repeatability is important. So we can contain failures and replay identical inputs. Second, controlled conditions. So we remove wind and GNSS uncertainty to focus on the controller. And third, quantitative instrumentation. So angle encoders and force torque sensor is implemented. So that provides us, how can I say, so enabling faster and more disciplined iteration. And next is objective. Our objective is to enable safe pre-flight verification and repeatable rapid tuning by integrating the FFT gyro with ArduPilot before the first flight. In short, we reduce first flight test risk through bench-side verification and tuning. Next is our approach. So we use Polybro flight controller and quadcopter running ArduCopter 4.5.7 through gimbal angle measurements. The vehicle's dynamic response can be observed. So, but we have some challenges. So first challenge is about position measurement. So because translation is constrained on a gimbal type stand, so position changes are not directly observable. To run GPS modes like loiter mode, we add a force and torque sensor and compute a virtual GPS signal for the first flight controller. And it supplies a position stand on the bench, allowing GPS mode logic to work. And second challenge is about acceleration. So specific force is measurable on the stand, but differs from free flight due to fixture reaction forces and added inertia of the gimbal frame. So as a temporary measure, we relaxed EKF3's observation noise and gating thresholds to suppress EKF errors. Of course, a proper correction is planned. So for example, ultimately, in injecting simulated IMU's acceleration signals would be ideal for consistency with the EKF. So next is system architecture. Here is the data path. We replay RC inputs or simulate RC inputs to ArduPilot, and angle encoders provide gimbal angles, and force torque sensor provides forces and torques. A host application computes a virtual position and injects it via Mavlink GPS input message. Yes. So next is evaluation test. Our evaluation has two steps. So first, a free flight test in stabilized mode. RC inputs are logged and pose is measured via motion capture system. Second, FFT gyro test. We mount the airframe and replay the exact same RC inputs in stabilized mode. Ideally, the pose derived from encoders and FT sensor or torque sensor data should match the free flight baseline. And this is the result of our first test, free flight baseline. And this slide shows the free flight baseline reference trajectories and attitude. These logs defines our ground truth for subsequent comparisons. They are the target behaviors we aim to reproduce on the FFT gyro. And this is result 2. So this is FFT gyro response. On this stand, the outer frame's moment of inertia has a large impact on rotational dynamics, and we observe slower response and phase lag relative to free flight. So this indicates added inertial loading from the gimbal frame, which reproduces dynamic fidelity unless compensated. Yes. And so because of the inertia effect, we constrained individual gimbal's axis, roll axis and yaw axis, and observed the response. So this confirms that frame layout and inertial distribution materially affect fidelity. Yes. And this is a result about thrust. So thrust derived from the FT sensor deviates by about 13% versus the free flight baseline. This quantifies the known gap we need to close. We believe this gap is mainly due to gimbal frame induced thrust loss. And next is this is additional test. We also run a neutral RC input test with no commanded motion in stabilize and outhold and loiter mode. In loiter mode, we observed oscillations likely driven by the frame's added inertia and signal latency. So in addition to inertia and inertia problem, there are some limitation. First, no ambient wind constraint. And second, sensor latency budget. And our future work is install actuators to reduce the effect of the gimbal frame's inertia and simulating an force and torque-based acceleration signal and injecting it to address the translation acceleration mismatch. So yeah, so if you are interested in this solution, please contact us. So thank you. Do you have any question? Yes, please.
We haven't got a roving mic, sorry, George.
Oh, yes. So thank you for your question. About the, how can I say, effect of the inertia, we observed some latency of the motion. So without frame, the copter should follow the target angle sharply, but with the frame, so there are, how can I say, huge. Yes, so that is very how can I say good question. So first to how can I say to make more suitable size frame. So I think also this frame is too large for this drone. And second is to implement some actuators to compensate the effect of the inertia. And yes, or we need very, very lightweight frame. Thank you.
Fantastic. That's an excellent talk. Oh,
So, and we have another thing to.
So finally, let me update the ArduPilot score with Randy. So in July, we had started the new ArduPilot score with D makers in San City, Korea. And we had the first trial session, 1-day session. First half is DIY session by D makers, and second one is flight mode programming education by Drone Japan. And finally, flying its new DIY copter with new flight. So I would like to expand such a kind of new curriculum more with you and based on your ideas. So please join in this drone ArduPilot score or with your ideas. Thank you so much for listening us. Okay, thank you so much. ありがとうございます。
Thank you for joining us for the ArduPilot Developers Conference 2025. With thanks to our sponsors, 3DXR, Aerosystems West, CUAV, QPilot, Hightech, Polybro, IR-Lock, KH Unmanned, Kraus Hamdani Aerospace, Maytech, Modal AI, Northwest Blue, SD Model, and Theseus. Organised by KH Unmanned. Hosted by 3DXR in North Yorkshire. Broadcast by Q Branch.